Yeah, there is a lot of math on the ACT. It's always good to review because there's all kinds of different concepts they can pull from. Geometry and algebra and pre-algebra and all that. Yeah. Are you allowed to use your calculator for all of the ACT? It's been a while. Yeah, that might be an important thing to know, Elijah, if you can use your calculator or not. All right. Looks like everybody is here-ish. Let's see. Daniel, Elijah, Greta, Caitlin, Mackenzie, and participant 2. Mysterious participant 2. So it's either James or Ruben, right? All right, so we'll go ahead and get started. The first thing I wanted to ask you guys is if you had any questions. So I know we've been covering a lot of material lately, and I know I think most of you have your Chapter 6 homework in, but I know that there's the test, and then we've started Chapter 7. So basically, any questions on anything we've done so far? Yes, I got your homework, Elijah, and we're good. I just didn't respond back yet. So anybody have any questions? You guys have all done all your homework, right? Wow, okay. That's all right. I appreciate the honesty. So just a quick kind of, do you guys want me to review 7.3 again, which was E, our new friend E? Or do you feel like you remember that? And you're ready to just get this done? All right, so we'll do a very quick review of E then. All right, so 7.3, we introduced just so I can get your comments, E. 7.3, we introduced a new concept, which was the value E, which is the Euler number, even though it looks like Euler when you see it written out. And E is a term just like pi, where we have an approximate value, but we can never say it is the absolute value. Yeah, Bueller. That's what I always think of when I think of Euler, but it's actually Euler. So here is our approximate value of E. E is about 2.718. And again, I apologize for the way it's written because it looks like this would just do 828182 repeating. But actually after this, then there's a bunch of other numbers. So it's not an exact number there. Okay, so what we wanted to know about E is, first of all, that it exists. It's an important concept if you want to work for Google, right? That's what we learned on Monday. No, I'm just kidding. It's actually an important concept for exponential growth and decay. The Euler number can be, see, I just said it wrong. The Euler number can be used to help us model some functions in science and math and exponential growth or decay. It also can be used for continuously compounding interest. So that's if your interest gets compounded continuously. We use the Euler number in the equation. Let's see, some other examples. I'm just looking at your book. In the book, the percent of light that filters down through bodies of water can be modeled by the Euler number equation. So I just said it wrong again. Euler. I know. E, I'll just call it E. So there's lots of different purposes for E. We just want to know that, one, it exists. So you want to know what that is. Thanks. Thanks for making me feel better. Two is how to use it. So there is on most calculators an E button, and usually it's by what we're going to talk about today in section 7.4. It's usually the E button. It usually looks like e to the x, is usually toggles with the natural log button, which we're going to talk about today. So usually these two buttons are close to each other, if not the same button on your calculator. Unless it's Desmos, then they're not right next to each other. But these two have a relationship, which we're going to talk about today. So all that being said, we can evaluate expressions that have E in them. And it's actually not so bad because we're going to use all of the same rules that we know for exponents and how do we deal with exponents to deal with E. So for example, if I have number 11 in your homework, and I have 3e divided by e to the x power, okay, and I want to simplify that, then what I'm going to do is I'm going to have to figure out, okay, I've got an e and an e to the x power. How can I simplify that? Well, we know that this could also be written as e to the first power over e to the x power, right? And by our rules of exponents, we can use the same rules just like this if this was x over x to the y power. I choose a bad variable there. We know that if we have an exponent divided by another exponent and they have the same base, we can just subtract, right? So it would be x 1 minus y. So the same is true here. This could be 3, nothing happens to 3. We have e, and we just subtract our exponents, 1 minus x power. So that's all you have to do. Use your same exact rules that we have for exponents and apply them when we have e as a base. Yeah, isn't that nice that the rules of one thing apply to the other thing? We've actually been doing these rules of exponents in chapter 5, 6, and now 7. So that is numbers. When you do 3 through 13, that's all you're going to do, the same thing that you did when you had exponents. No big deal. And then we have 19 through 30, and it says use a calculator to evaluate the expression. So this is complicated stuff here, right? So number 27, we have 2 times e to the negative 0.3 power. So how do we use a calculator to solve this? Let's go to here, I think. Yes, Desmos. Use your calculator. So if we go to Desmos, I don't actually know if there's a specific E key, is there? If I go into functions. I know you can just type in E. Nope, they don't even have a specific one. So you can just use your calculator or your keypad and do E. And Desmos knows what that is, right? So it tells you E is 2.71828182846, that big number. All right, so if we're doing number 27, we want to multiply it by 2, and then we want to raise it to the negative 0.3 power, and we want to evaluate it. So number 27, we would say that 2e to the negative 0.3 power is 1.482. Yep. So not too hard on that, right? And then the last 2 sections kind of homework that I have there assigned for you, it is pretty easy. The last 2 sections are to graph the function. Well, actually, 31 through 37 says, tell whether the function is an example of exponential growth or exponential decay. And then the last one says, graph the functions and state the domain and range. So we can kind of roll those 2 examples into one. So if we look at number 45, okay? So 45 in your homework says, I'm going to write it first so that we can kind of guess before we even look at it. Y equals 2e to the negative 3x minus 1. Okay, so when we look at this, do you expect this to be exponential growth or exponential decay, just purely based off of the equation? Or you have no idea? Oh, that's not what I wanted to do. There we go. Growth or decay based on the equation? Or don't know? The chat pod's not going crazy, so I'm guessing don't know. Greta says decay. I agree, Greta, because we have a negative exponent for our e, it's going to be decaying away, right? It's going to get smaller and smaller and smaller. So 31 through 37, you're really looking at the exponent and seeing if it's positive or negative. If it's positive, it's going to be growing. And if it's negative, it's going to be decaying. So now, Elijah, let's graph it. Y equals 2e to the negative 3x minus 1. Okay, so just a note here. So if I didn't put my negative in here, it's growing. See how I took the negative sign out? Put the negative in, it's decaying. That's the whole difference between growth and decay. Okay, so 45 says graph the function. So voila, we've graphed it. Yes, it's magical. All right. Part 2, state the domain and the range. Our favorite part, right? Actually, this class thinks it's easy. Like my last Algebra 2 class, every time we had to do domain and range. Oh, domain and range. So it's not a big deal, right? Domain is just your x's. Boo, range. It's not that bad. All right, domain is your range. Domain is your range. That didn't even make sense. Domain is your x values, right? So this can be any x value, even though this increases really quickly here. If you zoom out far enough, you can get any x value. So our domain is all, I think it's all real x's. I forget how we even say that. All real x values or all x or anything like that. Basically, any x value, right? Our range is a little bit trickier. Okay, so our range basically comes down here. If I can scroll along here, if it'll let me. There we go. All right, so our range is anything, oh man, messing this up. Our range is anything above 0 for y, right? And then when we get below 0, we get really, 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 really close to -1, but we never quite hit -1. So it would be all y's that are greater than -1. Okay? The place that can kind of get people tripped up, and if you're taking those ACTs, right, Elijah, is that if you look at your graph out here, it's going to tell you that the value is y equals -1, that you can actually get a value of -1, but you never can quite get to -1. And why is that? If you look back at your original equation, so the -1 is coming from this, right? So this is going to get really, 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 really close to 0. So if you put in like x equals 1,000,000, this is going to give you this tiny, 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 tiny number. I don't even know. I'm probably not even close. That is really close to 0, but not quite 0. So any x you put in is going to have some value for that. And that's why you can never truly get to -1. Yes, there is a term for that, Elijah. It's called the asymptote. Yes, the asymptote. So that's when your graph can get really, really close to a value, but never quite make it. So we would say the asymptote of this graph is at y equals -1. The one word you want to remember. It's kind of a weird word, so it's one of those weird ones when you hear it, you're like, yeah, the asymptote. Okay, so that was a review of 7.3. You guys should be able to do that easy peasy, right? So on to 7.4. Also not a bad section. I know you guys think that I'm lying when I say that, but really not a bad section. Because even though, this part you want to actually listen to me talk. Even though in 9 through 19 it says evaluate the logarithm without using a calculator, I am okay with you using a calculator. Just try to understand it, okay? All right, so you don't even know. You'll know. Okay, so what we're going to talk about is logarithmic functions. Okay, so there's a couple basics that I want you to know. And we talked about some of these on Monday. So a logarithmic function, the abbreviation for that is log. So you may have seen this also on your calculator before. And it is a way to help us basically evaluate these growth and decay functions. So by section 7.6, we're going to use logarithmic functions to evaluate things. But in 7.4, we're just going to learn what they are. Okay, so the definition of a logarithmic function is right here. Okay, so there's kind of this inverse relationship with expressions with exponents. So if y equals the log base b of x, then this works both ways. That's what this little sign means. B of y equals x. Like, Mrs. Ross, what does that mean? Why do we need to know that? Well, that's kind of the definition of what a logarithmic function is. And I think when you see a few written out, the log is a thing. It's an important part of math, but so let's see how it actually works, okay? So if I have the log base 3 of 81, if you were to evaluate that in your calculator, if you put in log base 3 of 81, you would get 4. Okay, and I'll show you how you can do that in Desmos. But basically what that means is that we have 3 to the 4th power equals 81. Okay, so what you're trying to find, like, what you're trying to find, let me do another one. It is basically flipping the equation, but a lot of times they won't tell you what it's equal to, Elijah. That's the tricky part. Okay, so let me clear this off because I made a mess of this page already. Okay, so if I have, for example, the log base 4 of 16, and I wanted you to evaluate that. Yeah, James, I'll get to that next too. So if I just gave you the log base 4 equals 16, and I want to know what that equals to, I'm going to use, no. I'll use y so I stay consistent with the formula up here. I want you to solve this. All right, Elijah's on the right track. I can actually use this relationship of logarithmic functions to solve it. So I can say, okay, 4 to the what power gives me 16? Yeah, the power. Yep, 2. So you don't even need a calculator for this, right? If I flip over to Desmos and I do log base 4 of 16, where are you, Desmos? All right. Functions. Oh, I can't even see. So you want this one that's log a because that means that you can put in a base. Log base 4 of 16 is 2. Okay? So let's look at a few of these other ones and kind of pretend like we don't know the answer so we can see how easy that is. So what I mean is if I have the log base 7 of 7, okay, log base 7 of 7, and I'm just going to pretend like I don't even know what that equals. I'll just say equals y. What I'm really looking at is 7 to the y power equals 7. So 7 to the what power equals 7? That means that y has to be 1, right? And big surprise, if you evaluate that, you get 1. Okay, so let's do another one. The next one is 14. Yeah, it looks easier than you thought, right, Greta? This part is easy. We're just learning what logarithms are. Okay, log base 14 of 1 equals y. I know that I have the answer written there, but so this means 14 to the y power equals 1. It is going to be what it is in the book, Elijah. So that just means that 14 to what power equals 1? That means y has to equal 0 because anything to the 0 power is 1. Okay, and then one more, if my computer will let me. Okay, we have log of 1/2, or log base 1/2 of 32. This one's a little trickier. This is where you might want to bust out your calculator, right? So equals y. So what this is 1/2 y equals 32. So this one you might not know off the top of your head. So the solution for y here is negative 5th power. Okay, so what that basically means is that you're going to get, since this is 1/2 to the negative power, you're going to get 2 to the 5th power equals 32 to solve. Because you're negative, oh, I just lost you guys. Okay, if I have 1/2 to the negative 5th power, I can rewrite that as 1 to the negative 5th power over 2 to the negative 5th power. 1 to the negative 5th power just becomes 1, 2 to the negative 5th, right? And then when we have a negative exponent, we can flip it to positive by putting it in from the denominator to the numerator. And then I get 2 to the 5th power. Sorry, that wasn't very well explained. All right, this one, log base 1/2 of 32, I wouldn't necessarily expect you to solve that out. So numbers 3 and 5, you just have to rewrite the logarithmic function. And then the rest, we're just going to evaluate using a calculator. I just want you to understand what the concept is. There's not far too many rules. There are some special cases which James pointed out, and I also did kind of give you a sneak preview of on Monday. Okay, so these are special cases for the logarithmic function. The first is the common log. Okay, so when you have Monday was the day of the week. Oh, James too. All right, so one of the common logarithms that you'll see, and this is on your calculator when you just see log without the little base, okay? What that means is that they are assuming, I'm trying to erase. All right. Well, my thing's giving up. Okay, so when you just see, like, for example, log of 12, and you're like, Mrs. Ross, you just taught me that this is the base to an exponent equals 12, and there's no base here. When you see that there's no base, it's an assumed base of 10. And this kind of makes sense because a lot of our exponential numbers have a 10 to a certain power. All right, so this is a really common, your chats are distracting me. All right, come back here. Come back to math. All right, so this makes sense because a lot of times we use, 10 to the second power or 10 to the fifth power. We use this in when we use scientific notation. It's a common terminology, so that's why this is called the common log. Okay, so what does that practically mean? It practically means that, I'm gonna get my computer to work. If you see a problem like number 7 where you have log of 12 and you're like, oh, they didn't give me any base, that means you're trying to find, and this equals y, right? You're saying 10 to the what power gives me 12? Is what you're trying to find, okay? And this you probably don't know off the top of your head, so that's why a calculator is going to help you out, right? So if we switch over to Desmos, maybe. All right, this is where when you look in your functions, there's a log and then there's a log-based A. So you just want log of 12, okay? Or I guess if you would have used the other one, you would just put base 10 in. So if you do log base 10 of 12, they both give you the same answer. Okay. So what this means is that log of 12 is 1.079. Okay. Yeah, about 1.1. And so what that means is if I put 10 to the 1.079 power into Desmos, right? I should get 12. So there's this relationship back and forth. That's the important part of this. I want you to understand there's a relationship. 10 to the 1.079 power. And if I keep going, 1, 8, 1, 2. So you see for every number I put in, I get closer and closer to 12. It's so close, right? So that's how the relationship works with each other. Is that when you take the logarithmic function, you take the log, then you have this relationship with the exponent. It's within the, I agree, it's within the margin of error, right? You got to like copy and paste on that. So it should not come as a surprise if I did 10 to the log of 12 power. And yes, you can do this. I don't know if you write log. Oh, you can even write log in. If you do 10 to the log of 12 power, then you get back to your original 12. So it's kind of all interrelated there. So let's do a few more of these. Okay, so that's, before we do that, that's one special logarithm, okay, is the common log where you have a base 10. The other one is called the natural logarithm. Okay, and this one actually does confuse people. So if you have, so the first one, the common logarithm, was basically log base 10. We rewrite that as just log. Yes. If you have the logarithm logarithmic function and the base is e of some number, okay? We can rewrite that as the natural log of x. So this confuses people. This ln, you're like, where did ln come from? It's probably some, you know, German name since Euler was German. I don't know. Yes, some natural logs. So if you have a log-based e, they're not going to write it as log-based e of x. You're going to see it written as the natural log of x. And this is a special function on your calculator. See? That's kind of a crazy looking picture. Yeah, I don't know. I didn't name it, that's for sure. Okay, so if you go under your miscellaneous, you'll see they're all kind of written here next to each other. You have, this is the log with a base of 10. This is a log with a different base. And this is your natural log right here. All right. Fancy pointed E. I'm not sure where you're looking at. Middle bottom. This thing? No, that's for calculus. That's when you have from this one, middle row all the way down. Oh, this thing? Sigma? Nope, none of these guys. You don't want any of these guys. Unless you're doing calculus, you don't want any of these guys. The only thing I don't know, yeah, you get to use fancy letters for calculus, that's for sure. I don't know what this is. X, E. I don't think that's right. No, that doesn't look right. Just use E. Okay, so let's do our last few examples so I can actually get you guys out of here on time today. All right, so in your homework, I have you doing not that much. Let's see, 3 through 27. So basically, you're going to use a calculator for 9 through 27. But as you're doing it, I want you to actually see if you can kind of understand what you're doing, not just blindly typing it in. Okay, that's the goal here. So we have log base 2 of 32. Okay, so let's do a couple of these. We have log base 2 of 32. So before we just blindly type this into Desmos, what we're trying to find is, we'll say equals y, right? We're trying to find 2 to the y power equals 32. And some of you guys might even know this. What 2 to what power gives you 32? 5. There you go, Greta. 2 to the 5th power equals 32. So we would expect when I type log 5, this should say 5. When I type this in log base 2 of 32, I would expect to get 5. So log base, trying to be slow. No, that doesn't work. You got to actually use the function. You can just use, yeah, you don't even have to use your calculator. Some of them are easy enough. You're just like, okay, I know what that is. Log base 2 of 32, voila, equals 5. Fancy, fancy, right? So that is the first one. Let's see what we got next. Log base 27 of 3. So that's why I'm saying you can use your calculator, but just use your brains too. Log base 27 of 3 equals y. There is no catch. This is it. The catch is we're going to learn how to use this in 7.6. How's that? There's no catch for 7.4. This is it. So this means it's just easy. I know. Just enjoy it. 27 to the y power equals 3. All right. So what do you guess your y is going to be? In order to get 27 down to 3, we're going to have to reduce it, right? You guys are crazy. 27, I'm guessing it's going to be, and I don't know, I'm guessing it's going to be to the 1/3 power. I just feel like that's right. Right? Because you need to have a fraction in order to reduce a number to 3. Yeah, but we're not just dividing, right, Elijah? It's something to the power. Yes. So we could actually even check it. If we wanted to kind of play with numbers. We could say 27 to the, I really feel like 1/3. Oh yeah, 1/3 power. See if it's to the 1/2 power, it's going to do that. Yep, that's the cube root. Okay, so then if we wanted to check it, right, we're going to just use Desmos. Log base 27 of 3.3333333. It's a cube root, not a square root. All right. Close enough, right, Elijah? All right, so let's try our next example here. Log 12, we did that one. All right. Natural log of 0.75. So again, you're going to see this in like, don't forget in 2 chapters what ln means. Natural log spelled backwards, right? Now I have 3 decimal points. It's not working for me. Trying to make it into one big decimal point. Okay, this one I don't know off the top of my head, but I know what it means practically. So I want to know e to what power gives me 0.75. Lateral log. There we go, Greta. We'll just start calling it that. That won't confuse me at all. So really, practically what we're trying to find is e to what power gives me 0.75. So let's just see. E to the second power, that's not going to work. Putting bigger and bigger numbers isn't going to get me to 0.75. So I am trying to get to 0.75. So I'm guessing it's like e to the 0.5 power. Nope, smaller than that. Smaller than that. Smaller than that. All right, I'm not doing a very good job guessing. So in this case, I can just go straight to evaluating, and I could say, all right, what's the natural log of 0.75? Oh, it's negative. That's why I wasn't getting it. So that means that if I do e to the negative 0.28768 power, right, the inverse of that, that I get 0.75, close enough. So that's it, no tricks. There is additional stuff in your book, like for example, using inverse properties simplify the expression. So I can just show you one of these. You don't have homework in this, but for example, number 31 says if I have so again, this isn't in your homework specifically, but you can probably figure it out. If I have 10 log of 8, okay, so let's think about what this means. Hold up. If we don't need to know, you're just going to ignore it. So if you remember, we've got log base B. This is, yeah, it's kind of like a puzzle, right? I mean, you could just also type this in. Log base B of y equals x. That means B of x equals y. I think I wrote those wrong. But anyway, so this looks like this equation, right? I just crossed over my 10. So B is 10 and x is log of 8. So I could rewrite this as log of 8 of y equals, no, log of 8. I'm totally messing this up because I have my x and y's messed up. Yes, I am totally messing this up. Let me start over. Scratch that. Go back to the equation. This is what happens. 10 log of 8. Okay. The way we have it written in our notes, I'm confusing myself with the x's and the y's from our notes. The way we have it written in our notes, yeah, let's stay over here. We have it written like this. Y equals log base B of x, and that's similar to B of y equals x. So if you look here, we've got 10 log of 8 equals x. We look like this expression. So that means that our B is 10 and our y is log of 8. So now let's write it in this form. Okay, so we end up with log of 8 equals log base 10 of x. Yeah. And then we have to divide both sides by the log of 10, and we'll figure out what x is. All right, so maybe I shouldn't have even gone there. The other option is that you could just say, all right, I want to know what 10 to the log of 8th power is. And we just get 8. Should have just quit while I was ahead, huh? I am lost. All right. I feel like I'm losing you guys here, so don't worry about that part that I just did. We'll talk more about that later. Is that all right? We'll start back up with that next time. I'm watching your chat here. You actually don't even need to do the homework for that right now, so I was getting a little ahead of myself. I was too excited about all of the logarithmic functions. All right. So right now, just worry about evaluating the logarithmic and natural log functions. And then as you're doing it, don't just type them all in your calculator. Say, oh, okay, that makes sense. You know, if I have the log base 2 of, or the log base 4 of 16, that means that it's going to equal 2. Yes. Do the easy logs and we'll get to the dividing by logs and all that funness later. Because I didn't do a very good job explaining it either. All right. And we're actually done early. Unless anybody has any questions. I don't know who James 2 is. Is there a mysterious James 2? All right. Well, that is all I have for you guys today. So thank you so much for coming. And we'll keep, so this is the beginning of logarithmic functions, and then we're going to talk more in 7.5 and 7.6 about things that we can do with logarithmic functions. When is the chapter 7 homework due? So next week we have class, and we will finish chapter 7 next week. And then the following week is when I'm out. So technically it's due on the 13th. I would tell yourself it's due on the 13th. How about that? But honestly, I won't be back until the 21st. Someone's making the screen go crazy. All right. That's it, guys. Have a good day. Bye. You may. It's Friday. You have to have a good day.